Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 17th lecture, and we're still talking about Riemann-Stieltjes disintegration, and today we're going to move to Riemann-Stieltjes disintegration of vector value functions, and here's the definition for a vector value function to be Riemann-Stieltjes disintegrable. It says let f sub 1, f sub 2, all the way up to f sub k be real functions on A to B, and let f bar be defined by the f sub 1, f sub 2, comma, all the way up to f sub k. And so this be the corresponding mapping of A to B into RK, and then we're going to suppose if alpha is monotonically increasing on A to B, okay, to say f bar is an element of the Riemann-Stieltjes integral functions with respect to alpha on A to B, means that f sub I is an element of the Riemann-Stieltjes integral functions with respect to alpha on A to B, and for, I should say, for I equaling 1, 2, all the way up to k. In this case, we define the integral of this vector value function with respect to alpha from A to B as the tuple, the k tuple, whose each entry, so the first entry is f sub 1 d alpha, second entry is the integral from A to B of f sub 2 d alpha, and so forth, all the way up to the integral from A to B of f sub k d alpha. As all definitions are, this definition is an if and only if statement. So if each individual components are Riemann-Stieltjes integral with respect to alpha, so is the vector value function, and if the vector value function is Riemann-Stieltjes integral with respect to alpha, then so are each one of its components, and we have this definition. And in other words, we can say, this is straight out of the text, this Riemann-Stieltjes integral of the vector value function f, so f bar d alpha, is a point in RK whose coordinates are the integral of f sub j d alpha as a the interval runs from A to B. What I'd like to tell you is that theorems are many theorems that apply to real value functions on A to B. In terms of integration, have analogous statements for vector value function. Vector value functions. F bar. And I'm going to list most of those theorems that we've had before, and their analogous version for F bar, but I'm going to state to prove one of them. So as an example, is a theorem if F bar goes from A to B into RK is, and I should say, F bar is an element, Riemann still is an integral function with vector alpha on A to B, and C is a real number. Then C times F bar is a Riemann Stieltjes integral function, and the integral from A to B of C F bar d alpha is going to be equal to C times the integral A to B of F bar d alpha. Let's look at this proof. So here, we let F bar be an element of Riemann Stieltjes integral functions, and C be an element of real numbers. And let's go ahead and denote F bar by, it's equal to F1, F2, all the way up to Fk, these functions. So what we know is since F bar is Riemann Stieltjes integral, then Fj is Riemann Stieltjes integral with respect to alpha. And that's true for j equal 1 all the way up to k. So each component function. Where am I still? Interval. And so, since the f sub j is a Riemann Stieltjes integral, then a constant times them. Is Riemann Stieltjes integral. And that's true by the previous analogous theorem, by a previous theorem. So, that means we have that CF1, I'm sorry. So that means that the integral from A to B, CF bar d alpha equals to the integral from CF1, A to B d alpha, comma, integral from A to B of CF2 d alpha, all the way up to the component that is, the k component that is the integral from A to B of CFK d alpha. And so each one of these is Riemann Stieltjes integral, making the overall vector value function Riemann Stieltjes integral. And then here, we pull out a C, and then times each one of these components. Which equals to C times the integral from A to B of f bar d alpha. And that's the proof. Okay. So we will now list several theorems involving integration of vector value functions without proof that's analogous to what we just did. Okay, for instance, we have the following theorem. It says, if f bar goes from A to B into Rk, f bar is an element of Riemann Stieltjes integral functions with respect to some alpha on A to B. And if A is less than C is less than D, then f bar is Riemann Stieltjes integral with respect to alpha on A to C and on C to B. And the integral from A to B of f bar d alpha will be equal to the integral from A to B, I'm sorry, from A to C of f bar d alpha plus the integral from A to C, sorry, from C to B of f bar d alpha. So that's one analogous statement. Here's another theorem. It says if f1 F1 and F2, F bar 1 and F bar 2. Let's just say F and F bar and G bar are functions from A to B into RK with F bar and G bar both being elements of Riemann-Stieltjes integral functions on A to B. Then F bar plus G bar is an element of Riemann-Stieltjes integral functions on alpha, with respect to alpha on A to B. And this integral from A to B of F bar plus G bar d alpha equals to the Riemann-Stieltjes integral from A to B of F bar d alpha plus the integral from A to B of G bar d alpha. Now this is something that I've asked you to do in homework, so it's left to the students to do this. Okay. Here's another theorem. It says if F bar is Riemann-Stieltjes integral with respect to alpha sub 1, and F bar is Riemann-Stieltjes integral with respect to alpha sub 2, then F bar is Riemann-Stieltjes integral with respect to alpha 1 plus alpha sub 2, and the integral from A to B of F bar with respect to alpha 1 plus alpha 2 is equal to the integral from A to B of F bar d alpha 1 plus the integral from A to B F bar d alpha 2. Of course, we're thinking F bar is a vector value function theorem. If F bar, the element of Riemann-Stieltjes integral functions, and C is some real number that's greater than 0, then F bar is an element of Riemann-Stieltjes integral functions with respect to C alpha, and the integral from A to B of F bar d C alpha is equal to C times the integral from A to B of F bar d alpha. Another theorem is assume alpha increases monotonically and alpha prime is Riemann integral on A to B. Let F bar be bounded, be a bounded vector value function on A to B. And it says, then F bar is Riemann still just integral with respect to alpha, if and only if F bar alpha prime is Riemann integrable. Okay, here's another analogous statement. Theorem. If F bar and big F bar map A to B into RK, F's an element of Riemann integrable functions on A to B, and I'm sorry, I skipped it there. Let me back up. Okay, let F bar go from A to B into RK. Suppose F is Riemann integral on A to B, and then for A less than or equal to X less than or equal to B, put F bar, big F bar, of X equal to the integral from A to X of F little f bar t dt. Then big F is continuous on A to B. Okay. Furthermore, if F bar is continuous, little f bar is continuous, at some point x naught, element of A to B, then F bar, big F bar, is differentiable at x naught, and big F bar prime at x naught is equal to little f bar evaluated at x naught. Of course, this statement is the fundamental theorem of calculus part 1 for vector value functions. Okay. The next statement says if little f bar and big F bar map A to B into functions on A to B, and if f bar prime equals to little f bar, then the interval from A to B of little f bar t dt is equal to big F bar evaluated B minus big F bar evaluated A. This is the fundamental theorem of calculus part 2. Okay. The next thing I'm going to do is list an analogous theorem, something we had, but its proof is slightly different than just applying to each component. And so I'm going to provide that. This is straight out of our text. So I'm going to provide the proof. Theorem. It says if f bar goes from A to B into RK, and if f bar is Riemann-Stieltjes disintegrable with respect to some alpha, for some alpha, that is monotonically increasing on A to B, then the norm of f bar, that's the norm, is Riemann-Stieltjes integral on alpha, and the integral from A to B of f bar d alpha, the absolute value of that, is going to be less than or equal to the integral from A to B of the absolute value. This is the absolute value. This is the norm of f of t, let's just say f, d alpha. Okay, so the proof. All right. Well, we let f bar be equal to its components f1, f2, f3, all the way up to fk. Then f bar norm is equal to the square root of f sub 1 squared plus f sub 2 squared plus all the way up to f sub k squared. Square root of that. Now, since f bar is an element of Riemann-Stieltjes integral functions with respect to alpha, then f sub j will also be elements of Riemann-Stieltjes integral function with respect to alpha. And that's true for each, for j in between 1 and k. Okay. So, by previous theorem, or previous work even within a theorem, that says that f sub j squared is an element of Riemann-Stieltjes integral functions. For 1 less than or equal to j less than or equal to k. Now, since fj Fj is Riemann still disintegrable, then Fj is bounded and here let's say it's squared. Okay? It's true for that. The square is also bounded. So then this sum of f sub 1 squared plus f sub 2 squared plus f sub k squared is also bounded, say by m. Okay. Since g of x equaling to the square root of x is continuous, on zero to m, then what we can say that the square root of f sub 1 squared plus f sub 2 squared plus f sub k being squared, which equals to the norm of f bar, is Riemann still disintegrable function with respect to alpha as f1 squared plus all the way up to fk squared is Riemann still disintegrable with respect to alpha. Because if you add a bunch of Riemann still disintegrable functions with respect to alpha, you get something that's Riemann still disintegrable function. Okay, so what that just showed is that the norm of f bar is Riemann still disintegrable. That's wonderful. That's part of the theorem. The other part of the theorem is to show an inequality between the integrals. The absolute value of the integral and the integral's absolute value of the function, or the norm of the function. So we'll work on that next. Okay, now we want to prove that the absolute value of the integral from A to B of f bar d alpha is less than or equal to the integral from A to B of the norm of f bar d alpha. Okay, so we'll do this with some notation. We'll let y bar be equal to y1, y2, all the way up to yk, which really is equal to the integral from A to B of f1 d alpha, comma, the integral from A to B of f2 d alpha, all the way up to the integral from A to B of fk d alpha. And of course, that's equal to the integral from A to B of f bar d alpha. So, that's what y bar is. Now, note, the norm of y bar squared, by the definition of this norm, is really the sum of the yj's to be squared. Say j runs from 1. I used I, so I'm going to keep that. As I runs from 1 to n. Now, this can be thought of as the sum as I runs from 1 to n. Here I'm going to leave this as y sub I. But then times y sub I, which I'm going to rewrite as what it is the integral from A to B of f sub I d alpha. And now, what I'm going to do is essentially, you pull in the y sub I if you want to. It's just like it's a constant, and you can pull it out and pull it inside the integral. And the sum of the integration is really the integration of the sum. So here, this is going to be the integral from a to b of the sum as I run from 1 to n of y sub I times the integral, times L sub I d alpha. Okay, now what we're going to do is look at just this sum for a minute. But first we're going to look at it by using the Schwarz inequality. And so let's recall the Schwarz inequality. Here's what it says. It says if A1, A2, all the way up to AN, and B1, B2, all the way up to Bn are complex numbers, then we have the following inequality. That is that the sum is, let's say maybe I runs from 1 to n, of AI times BI conjugate to be inside absolute values, or norm here, to b squared is less than or equal to the sum as I runs from 1 to n of the norm of a sub I to b squared times the sum as I runs from 1 to n of the b sub i's to b squared. So if we look at the sum that we're integrating, well, let's look at the absolute value of it first. This guy is less than or equal to, so the Schwarz inequality had something of this nature being squared. Okay? Where these are, real value functions. So here we don't have to have the conjugate, or the conjugate is itself. And so it's going to be equal to the square root of this sum of the yi to be squared times the sum of the f sub i's. There. Norms to be squared. So those are absolute values there. All right? And so if we look at the sum without absolute values, that's going to be less than or equal to the square root of, well, the absolute value of something squared is just that quantity being squared. The sum, as I runs from 1 to k, of yi squared. And similarly, this is the sum as I run from 1 to k of f sub I squared. So this sum is less than or equal to, this quantity is the norm of y to b squared. And this quantity right here is the norm of f bar to b squared. And so that's equal to norm of y times the norm of f bar. And I'm saying this for f bar, really, this is really being applied to any t for any t in between a and b, because that's where f bar works. Okay. So, what we have then is that the norm of y bar to b squared is less than or equal to the norm of y bar times the norm of f bar of t. And so we can break this into cases. First case is if the norm of y bar is different from 0. And then our preceding inequality, we can divide both sides by the norm of y bar. And so we get the norm of y bar is less than or equal to the norm of f of t. Okay. So, now we'll go from a to b of f bar d alpha will be less than or equal to the integral from a to b of f of t bar. Student bar here. D alpha. And that's what we wanted to show. Remember, y bar here, what I should have written, is nothing more than the integral of a to b of f d alpha. So this stems from a practice we've already had. And this this interval is less than, that's the value of the other one. Okay, so case 2, if y bar equals to 0, then what we have is that this integral from a to b of f1 d alpha, integral from a to b of f2 d alpha, all the way up to the integral from a to b of fk d alpha, that's equal to zero, 0, 0, 0. So what we're saying is that the integral from a to b of f of t bar d alpha equals to 0. That's what we're saying. So since 0 is less than or equal to absolute value from a to b of the absolute value of f bar d alpha, then the absolute value a to b in this case of f bar of t dt, which we know that that's just going to be equal to 0, is going to be less than or equal to the interval from A to B of f bar d alpha. And so, in all cases, we have the integral from A to B of f bar d alpha, the absolute value of that, is going to be less than or equal to the integral from A to B of the norm of f bar d alpha. And that concludes the proof. We're now going to turn our attention, for the last part of this lecture, just for a few more minutes, to a topic that is of interest for complex analysis. And so here's the first definition to look at. It says a continuous mapping gamma of an interval A to B into RK. This work is going to be listed for these mappings into RK, but for complex analysis, we'll be interested in R2. They will be. Is called a curve in RK or sometimes it's called a curve on A to B. That's our first definition. And here's another definition. If a curve gamma is 1-to-1, then gamma is called an arc. That's a particular type of curve. Here's another definition. If gamma is a curve and gamma of A equals to gamma of B, then gamma is called a closed curve. A few more definitions will come what's there. Okay, associated to each partition A to B and each partition of A to B say script P equal to x sub 0, x sub 1, all the way up to x sub n. and each curve gamma on A to B is a number, capital lambda, of this partition with respect to this curve gamma, defined by lambda of the partition with respect and lambda of the partition gamma is equal to the sum as I runs from 1 to n of gamma of x sub I minus gamma of x sub I minus 1 inside absolute values, which we will call the sum of the distances between gamma of consecutive partition points. I might have said the absolute value here. Really, this is the norm, so that needs to be corrected. We next make two definitions. The length of gamma, a curve on A to B, is, so it's lambda of gamma, which equals to the sup over all partitions of this lambda of P gamma, which we just previously defined. And here's the last definition. It says if this lambda of gamma is less than infinity, so some number, then we say gamma is rectifiable. Okay, ladies and gentlemen, that's enough for this lecture. Thank you very much.